Ever wonder how they get all those tiny details etched onto glass? Like on awards or even inside some tech gadgets.
Mm-hmm.
Or how about those computer chips? They just keep getting smaller and more powerful. It's kind of mind-blowing, right?
Yeah, it really is.
Well, both of those things, they actually rely on this technology that honestly seems like something straight out of science fiction ultrafast lasers. We're talking about pulses of light so incredibly short.
So short.
Yeah, that they can actually etch materials with atomic precision.
It's amazing the level of control that we have now.
It is. And the research we're diving into today, it actually reveals this really surprising twist. It turns out there's this hidden player in this whole process. You have this subtle after effect of each laser pulse that can drastically change what we get in the end.
See, this is what I find so fascinating. We often think of lasers as, these really powerful tools, right? Just raw energy.
Yeah, brute force.
Exactly. But with ultrafast lasers, we're entering this whole other realm of subtlety.
Okay, so let's break this down a bit. What exactly do we mean by ultrafast when we're talking about lasers?
Okay, so we're talking about lasers that operate on femtosecond timescales.
Femtoseconds, okay, that sounds short.
Super short. To give you a sense of just how quick that is, imagine light, and light is the fastest thing in the universe, right? Imagine it could only travel the width of a human hair in that time frame.
Wow.
That's the level of speed we're dealing with here. And it's the speed that lets us interact with materials in ways we simply couldn't before.
It's like having a scalpel that can operate on individual atoms.
Exactly. And that's what makes this technology so incredibly powerful. It's not just about making things smaller. It's about manipulating matter at its most basic building blocks.
So obviously, this goes way beyond your everyday laser pointer then. Where are we actually seeing the real-world impact of these ultrafast lasers?
Oh, this tech is popping up everywhere. It's completely changing the game in a bunch of fields. Manufacturing is a big one, of course. You need incredibly precise components for things like electronics, medical devices, even aerospace tech.
It does.
Yeah, and it all comes down to being able to control those lasers with unbelievable accuracy.
Which is what we're going to be talking about today. We're focusing on one particularly cool application, laser etching. So how do we go from these insanely short laser pulses to, say, etching a super detailed design on a piece of glass?
It's all about focusing that immense power.
Okay, so like a magnifying glass.
Kind of. Picture using a magnifying glass to focus sunlight onto a leaf. But in this case, instead of just burning the leaf, we're using the laser's energy in a much more controlled way.
To do what?
To create these teeny tiny modifications within the glass itself.
So instead of removing material, we're actually changing the glass itself, like its properties.
Exactly. The energy from that laser pulse, it interacts with the glass and actually changes its properties at a really fundamental level. Like it can change the refractive index.
Refractive index.
Yeah, so that determines how light bends when it passes through the glass.
Oh, okay. So by controlling exactly where the laser hits, we're basically drawing patterns within the glass.
You got it. And get this, by precisely controlling how we move that laser, think of it like a supercharged 3D printer, but on a way smaller scale, we can create all sorts of patterns and structures inside that piece of glass.
And this is where it gets really, really cool, because it's not just the laser pulse itself that's doing the work. The research we're digging into today, it focuses on this, I don't know what to call it, almost like a hidden aspect of these ultrafast lasers.
Okay.
Something called the pulse pedestal.
Ah.
So first of all, what even is a pulse pedestal and why is it such a big deal?
You see, the ideal scenario would be a single, perfectly clean burst of energy from the laser.
Oh, okay, like a really quick snapshot of light.
Exactly. But in reality, laser pulses often have these low-intensity pedestals of light that come either before or after the main pulse.
So like the afterglow of a camera flash?
Perfect analogy.
But you're saying even though those pedestals are, tiny compared to the main pulse, they can still mess things up.
That's the thing, they can. And it seems counterintuitive, right?
It does.
You'd think that powerful main pulse would just overpower everything else. But it's all about something called pulse temporal contrast. Basically, the ratio between how strong that main pulse is, how strong the pedestal is.
Okay.
And researchers are finding that even if that pedestal is really weak, it can still make a big difference in how that laser interacts with the material.
So it's not just about blasting the laser. It's about controlling those tiny details. It's about finesse.
Exactly. And to really get a handle on how this pulse pedestal changes things, the researchers over at the University of Southampton, they did a really cool experiment. They used two different lasers. One of them was able to deliver this high contrast pulse. So that's the clean, powerful pulse with almost no pedestal.
Got it, the ideal one.
Right. And then the other laser, it had a low contrast pulse. So that means it had a much more noticeable pedestal.
So they essentially had a clean laser pulse and one with a bit of an afterglow effect.
Exactly. And they used both of them to etch glass, making sure that everything else about how they used the lasers stayed exactly the same.
Smart.
Yeah, that way any differences they saw in the etching, it would only be because of the difference in that pulse contrast, how big that pedestal was. And you know what? The results were pretty wild. Even though both lasers were hitting the glass with the same amount of energy, they ended up causing really different changes.
Okay, so two lasers, one with a clean pulse, one with that afterglow pedestal, both etching glass. What did those differences actually look like? Paint me a picture.
Okay, so the high contrast laser, the one with the clean pulse, it created these things called, get this, flattened nanopores.
Flattened nanopores.
Yeah, so basically imagine these tiny, perfectly formed pits etched into the surface of the glass. And we're talking crazy small here, like billionths of a meter.
Okay, so it's almost like using that laser scalpel to make a super precise cut. What about the low contrast laser then? How did that pedestal change things up?
All right, so this is where it gets extra interesting. The low contrast laser, the one with that more prominent pedestal, it created something totally different. Instead of those little pits, it made these elongated structures. They're called lamella-shaped structures, almost like tiny ridges that formed inside the glass. Totally different from the high contrast laser.
So same material, same total energy from the laser, but whether or not that tiny little pedestal is there completely changes the end result. Mind-blowing. But, okay, why does this even matter? Is one of these modifications actually better than the other?
It's not really about one being better. It's more like having the right tool for the job, Like you wouldn't use a hammer to try and put in a screw, right?
Right, of course.
Each tool has its purpose. So in this case, being able to choose between making those nanopores or those lamella-shaped structures, well, that gives us a ton of control over how that material ends up behaving.
So it's all about tailoring the outcome then?
Exactly. Like, for example, those nanopores that the high contrast laser makes, those tiny, well-defined pits, those could be perfect for making those high-density data storage devices.
Really?
Yeah. Think about it. You could etch billions of those tiny nanopores onto a piece of glass that could fit in your hand. Each one of those could store a bit of information.
That is pretty wild. We're talking about storing an insane amount of data on something you could just slip in your pocket.
Yeah.
What about those other structures then? The ones from the low contrast laser, what could those be used for?
Those lamella-shaped structures, those are super cool. Because of their shape and how they interact with light, they could be amazing for guiding light in very specific ways.
Okay, so like fiber optics.
Kind of, but on a much smaller scale. This could completely change fields like photonics, lead to much faster, more efficient optical communication and computing, all because of these tiny little structures.
So we can actually control the structure of materials with that much precision. That just blows my mind.
And it's all thanks to understanding these ultrafast lasers, especially that pulse pedestal we talked about. It really makes you wonder, where else could we take this? What other fields need this kind of control with laser etching?
Honestly, the possibilities are endless. Biomedicine is one that comes to mind.
Oh, wow. Okay, how so? Well, think about it. Imagine using these techniques to work on individual cells or tissues. We could repair damaged nerves, maybe by etching out this super precise scaffolding for them to grow along, or even deliver drugs to specific cells in the body.
So it's like we're going from using lasers as these powerful tools to almost like a surgeon's scalpel.
Yeah, but on a scale thousands of times smaller. It's incredible.
Absolutely incredible. And to think, this is just the beginning.
Oh, for sure. We're just scratching the surface of what's possible with ultra-fast lasers. As we keep learning more about how light and matter work together at these crazy fast speeds, who knows what we'll discover.
It really makes you look at things differently. Like you see something like an intricate engraving on a piece of glass, and you don't just see the design itself anymore. You see all the science that went into making it. It really makes you think about those engravings we talked about before, those intricate ones. Like, it's not just about someone designing something cool. It's about understanding the science to even make it happen. It's amazing.
Oh, totally. It's like art and science kind of blurring together, especially when you're working on such a tiny scale.
Yeah. And I think what's so cool about this research is it's not just about making things smaller or faster. It's really about changing how we interact with, well, everything.
Yeah.
We're not stuck with the same old tools anymore. We can literally work on things at the atomic level. And that just opens up so many possibilities.
And a lot of that comes down to this whole thing with pulse shaping, being able to understand and actually use something as small as that pulse pedestal.
Yeah.
It gives us this insane amount of control over what happens when the laser hits something. It's like having, I don't know, all these little dials and knobs that we can fine-tune to get the material to do exactly what we want.
It's like we used to think of lasers as these powerful tools, but kind of blunt in a way,
Right.
But now we're realizing just how precise they can be.
Exactly. And the best part about science, in my opinion, is that with every new thing we figure out, it just leads to even more questions.
Which is always a good thing.
No, absolutely. It keeps things interesting. Like, we've been handed the key to this room we never even knew existed, and now we can't wait to see what's inside.
And to think, all of this whole deep dive, it came from this like tiny detail in a research paper. It just shows how even the smallest things can completely change how we see the world. So yeah, next time you run into something that seems kind of insignificant, take a second. Think about what might be hiding underneath. You never know what you might find. Okay, so lasers, right? Everyone loves a good laser.
Definitely. They have this cool factor.
But today, we're going deeper.
Deeper.
Much. We're talking about writing information inside of glass with lasers. Like not just etching the surface.
Oh, wow. That's incredible.
Yeah. This paper, Controlling Ultrafast Laser Writing in Silica Glass by Pulse Temporal Contrast, gets seriously granular.
So, ultra-fast lasers on glass, what's the big deal with this one?
It's about control. This paper shows how the tiniest tweaks to a laser pulse can totally change the results you get within the glass itself.
Okay, I'm intrigued. So we're talking about variations in the laser itself, not just aiming it differently.
Exactly. Think of it like two cameras, both look the same, but one takes perfectly sharp pictures, and the other, well...
The other has that weird blur, right? Like a ghost image.
Exactly, a ghostly echo. And that's kind of what this pulse pedestal is. It's this tiny bit of extra energy that can hang out behind the main laser pulse.
And this impacts how the laser interacts with the glass, even though it's such a short burst.
We're talking femtoseconds here, right?
Femtoseconds. 1/4,000,000th of a second. Imagine trying to take a picture of a hummingbird's wings, frozen in mid-flap. You'd need a camera that could capture things on the femtosecond scale.
Okay, so crazy fast.
Ah.
But this echo, it actually matters at those speeds.
Absolutely. Think of it like trying to write your name in sand. A single gust of wind, not going to happen. But a really precise, controlled jet of air.
You could write a whole message.
Exactly. That pulse pedestal, that little echo, it's like that focused jet of air. It gives scientists so much more control over what happens inside the glass.
So they tested two lasers on silica glass, one with that echo and one without. What happened?
Night and day difference. The laser without the echo, it still did stuff to the glass, don't get me wrong, but it created these unbelievably tiny structures, like almost invisible even with a powerful microscope. We're talking nanopores here.
Nanopores, so like super tiny holes.
Essentially, yeah, like microscopic pores in your skin, but, in glass.
Okay, so laser 1, no echo, equals crazy tiny pores.
What about laser 2, the one with the echo? What did that do?
That's where it gets really cool. Instead of those nanopores, this laser made these much larger visible structures. We call them lamellae.
Lamellae. Try saying that 5 times fast.
Right, it's a mouthful. Think of them like layers in the glass, almost like a fancy pastry. All those delicate, thin layers. Okay, I can picture that. But why does the shape of these laser-made structures even matter? I mean, what can you actually do with them? So we've got these nanopores, like teeny, tiny, invisible dots, and then these lamellae, like layers, right? But why does the shape even matter? What can we do with these structures?
That's where the magic happens, right? It's all about how they interact with light. Those nanopores, for instance, because they're so small, they could be the ultimate filter.
Ultimate filter, okay. Like how?
Think air purification, water purification. We're talking removing stuff we can't even see.
Wow. Okay, so it's like a microscopic sieve built into the glass.
Exactly.
Okay, that's nanopores. What about the lamellae? Those layers, what's their superpower?
Light manipulation. They can actually change how light travels through them. Think polarized sunglasses, but like on a microscopic level, built right into the glass.
Okay, that's just cool. But the paper mentioned something else. 5D data storage. What is that? Is that even real?
It sounds like science fiction, right? But it's a real thing. And these structures might be the key to making it happen. The way we usually store data, it's all ones and zeros.
Right.
Like a digital Morse code. ...
Yeah, I vaguely remember that from school.
Exactly. But 5D data storage takes it to a whole new level. It's not just about ones and zeros. It's about using the physical structure of a material, in this case glass, to actually hold the information.
So instead of a line of ones and zeros, you're using the nanopores, the lamellae, those tiny structures themselves to represent data.
You got it. But it's more than just their presence or absence. It's about their size, their shape, how they're arranged, even how deep they are in the glass.
Okay, so it's like a super complex 3D code inside the glass itself.
Yeah.
That's insane. But how do you even read data like that?
Good question. We can't just hold it up to the light and see the information, right? That's where the magic of light comes in again. Remember how I said the lamellae can manipulate light?
Yeah.
Well, by shining a very specific type of light through the glass and seeing how it interacts with those structures, we can actually decode the information that's stored within.
So you're like reading a code made of light with light. My head hurts. But why go through all that trouble? Is it really that much better than what we have now?
Durability. Think about it. Glass is incredibly stable, or it doesn't really degrade like other materials. Heat, water, even most chemicals don't phase it.
Yeah. We don't make them like they used to, you know? I mean, people are still finding perfectly preserved glass stuff from like thousands of years ago.
Exactly. So imagine storing all of human knowledge on a piece of glass, bury it for future civilizations to find.
Like an ultra high-tech message in a bottle. Instead of like stick figure drawings, it's the entire Library of Congress encoded on a piece of glass.
It's a pretty wild thought, isn't it?
Yeah.
And the research suggests this kind of storage could last like billions of years. We're talking almost unimaginable stretches of time here.
Billions with a B. Okay, so we've gone from writing on a CD to writing on something practically immortal.
That's the idea.
Okay, so 5D data storage. Definitely bookmarking that one. But there was something else in the paper's conclusion, something about how these laser-created structures, they do even more with light, right? What was that about? So we've covered etching invisible patterns. We talked about filtering at like the nano level.
Yeah.
And then data storage that could outlive the solar system. What else can these laser-made structures do with light?
Well, the researchers discovered something really interesting. It turns out that depending on how light hits these structures, they can either absorb it super efficiently, like almost completely, or let it pass through without any interaction.
Wait, so these structures can be like, nope, not today, light, or come on in, the water's fine.
That's a great way to think about it, like a microscopic light switch built into the glass itself.
Okay, that's cool, but what could you actually do with that?
The possibilities are huge. Imagine designing windows that could change their transparency whenever you wanted.
Like automatic blackout shades. Sign me up.
Exactly. Block out all the UV during the day, then become totally transparent at night so you can see the stars.
That'd be amazing.
Yeah.
No more messing with curtains.
Or think about clothes that could switch from absorbing heat to reflecting it instantly.
So you could be out in the sun, stay cool, then walk into the shade, and boom, your clothes adapt.
Precisely.
We went from etching initials with lasers to, like, weaving invisibility cloaks. This research seemed so niche at the beginning. Now it's blowing my mind.
That's what I love about these deep dives. We start with one paper, and it opens up all these possibilities.
So for everyone listening, what's the big takeaway for you? The laser precision, 5D data storage, or maybe the future of light manipulation?
Whatever it is, I hope this sparked your curiosity. Because who knows, maybe you'll be the one to take this research even further.
This is definitely one for the bookmarks. Until next time, keep those brains switched on. We'll catch you later. All right, so get this. We're talking lasers today, but not just any lasers.
Oh.
These ones can literally sculpt stuff inside solid glass.
Wow.
It's like microscopic 3D printing, but instead of plastic, we're talking about using light to create these tiny, intricate structures.
Yeah.
Isn't that wild?
It really is amazing. Like when you think about the level of control we're talking about.
Yeah.
Imagine building something, not just atom by atom, but creating shapes and patterns within those atoms.
Right.
That's the scale we're dealing with here.
Wow.
And the implications are huge across so many fields.
Okay, so walk me through this.
Okay.
The research paper we're diving into today focuses on this thing called the pedestal of a laser pulse.
Right.
Now, I'm no laser scientist, but I'm guessing most people wouldn't think that's a big deal.
Yeah.
But this paper says it is.
You're absolutely right. The pedestal is often overlooked, but it turns out to be incredibly important.
Okay.
To understand why we need to think about the shape of a laser pulse.
Okay.
It's not just a simple burst of light. There's this specific structure to it.
Yeah.
You have the main pulse, which is like the powerhouse, the main event.
Right.
But often, right before that main pulse, there's this weaker lead-in called the pedestal.
So like an opening act before the headliner.
Yeah.
You might not show up just for the opener, but they can totally set the mood for the whole show.
Precisely.
Right.
And researchers are finding that this opening act, this pedestal, can dramatically change the final outcome when you're using a laser to modify materials.
Interesting. Okay. And in this case, they were using these lasers on silica glass, which, I mean, glass is everywhere, right? So what kind of differences are we talking about here?
Well, the researchers compared two types of lasers.
Okay.
A fiber laser and something called a YBKGW laser.
Okay.
Both operating at the same wavelength.
Okay.
Now, you might think that using the same wavelength would produce identical results, but here's where it gets really interesting. The paper shows that's not the case.
Wow.
These lasers created completely different structures inside the silica.
Wait, so same wavelength, different outcomes?
Yep.
That sounds kind of like using a ballpoint pen versus a calligraphy pen, right?
Huh?
The ink is the same, but the marks you make are completely different.
That's a great analogy.
Yeah.
And it all boils down to something called temporal contrast. Essentially, it describes the difference in power between that main laser pulse and its pedestal.
Got it. So how does this temporal contrast actually play out in the results? What did they see when they looked at the glass under a microscope?
This is where it gets really cool. Imagine being able to see these nanoscale structures with your own eyes.
Yeah.
The researchers used a special kind of microscope,
Right.
and the images they captured are mind-blowing.
And they actually show these differences in the paper, right? I was looking at figure 1 earlier.
Exactly. Figure 1 shows it beautifully.
Right.
The fiber laser, with its more prominent pedestal, created these long, thin modifications. They call them lamella-shaped structures.
Okay.
But the YBKGW laser, with its cleaner, higher contrast pulse, produced something closer to tiny, rounded nanopores.
Okay, so we're seeing two distinct fingerprints left behind by these lasers. But how does the pedestal specifically cause those long, thin lamellae to form? The paper mentioned something about self-trapped holes, or STHs, and honestly, that sounds kind of intimidating.
Right.
Right.
Don't worry, it's not as complicated as it sounds. Think of STHs like tiny weak points within the silica structure.
Right.
When that laser's pedestal interacts with them, it's almost like pre-weakening the material in very specific areas. Then when the main laser pulse hits, it's like it's following a blueprint that's already been laid down by the pedestal.
So the pedestal is like scoring a piece of paper before you fold it. The fold will naturally want to follow that line you've created.
Exactly.
Yeah.
And that pre-weakening guides the formation of those long, thin lamellae. Pretty cool, right?
Okay, that is seriously cool.
Yeah.
But I have to ask, so what? We've got these lasers creating different microscopic structures inside glass. But why should I, as a listener, care about this? What's the big deal?
That's the crucial question, right? And the answer is this isn't just about making cool shapes in glass. This level of control, being able to manipulate materials at such a tiny scale, opens up a world of possibilities. We're talking about the potential to revolutionize entire industries.
Right, you've got my attention. Give me some examples. What kind of revolutions are we talking about?
Well, one area they highlight in the paper is more precise laser machining. Think about industries that require incredible precision. Things like microelectronics, building the tiny components for our phones and computers,
Right.
or telecommunications, developing faster and more efficient fiber optic cables, even medical devices where they need incredibly fine instruments for delicate procedures.
Yeah.
This technology could be a game changer in all of these fields.
It's like going from using a chainsaw to sculpt something to using a microscopic laser scalpel.
Yeah.
You have so much more control over the final product.
Exactly. And because we're not just cutting or etching the glass, but actually manipulating its internal structure, it opens up avenues for creating materials with tailored optical properties.
Right.
Imagine glass that can filter specific wavelengths of light with incredible efficiency,
Wow.
or even guide light in very specific ways.
Yeah.
We could revolutionize everything from solar panels, making them vastly more efficient at capturing energy, to developing entirely new types of lenses for cameras and telescopes.
Okay, that's seriously cool. And the paper also mentions 5D optical data storage, right? I'll be honest, that one kind of blows my mind.
It's mind-blowing stuff. 5D optical data storage. essentially uses those microscopic structures within the glass to encode information in multiple dimensions. It's like cramming an entire library's worth of data onto a disk the size of a quarter.
Wait, a whole library on something the size of a quarter? How is that even possible?
It's all about how we encode the information. Imagine each of those tiny structures we talked about earlier, those lamellae and nanopores, as a bit of data. By arranging them in specific patterns within the glass across multiple layers and even using different orientations, we can store information in 5 dimensions. It's like having a whole extra dimension of bookshelves to fill up.
That's incredible. And it gets even better, right? I mean, data storage isn't just about how much you can cram, but how long it lasts.
Absolutely. And that's one of the most exciting aspects of 5D optical data storage. Because the data is stored within the physical structure of the glass itself, it's incredibly durable. We're talking about the potential for storing data for centuries, maybe even millennia, without any degradation.
No more worrying about your hard drive crashing and losing all your photos and files.
Exactly. And what this research shows is that by manipulating those structures even more precisely, by controlling things like the shape and orientation of the nanopores and lamellae, we could potentially pack even more information into even smaller spaces. Imagine a future where we have tiny, incredibly durable data storage devices capable of holding unimaginable amounts of information.
That sounds like something straight out of science fiction. But here's something else that I found really fascinating. The paper talks about how the laser light isn't just carving these structures, it's actually interacting with them, creating even more intricate patterns.
Right.
It's like the laser is having a conversation with the material.
That's a great way to put it. The researchers specifically discuss interference patterns, which are a fascinating phenomenon of light. You know how when you shine a light through a prism, it splits into a rainbow of colors?
Yeah.
That's because the different wavelengths of light bend at different angles.
Yeah, I remember learning about that in school.
Well, something similar happens here, but on a much smaller scale. As the laser light interacts with those tiny structures it creates within the glass, it generates these interference patterns. Certain areas will become brighter while others become darker, and those patterns in turn influence the formation of even finer details within the glass. It's almost like the laser is sculpting on a scale even smaller than itself.
So we've gone from lasers carving structures in glass to those structures shaping the light itself, which then creates even more intricate structures. It's like a microscopic feedback loop.
Precisely. It's a beautiful example of how light and matter can interact in unexpected ways. And by understanding these interactions, we can unlock even more precise and sophisticated ways to manipulate materials at the nanoscale.
This whole thing just keeps getting wilder the deeper we dive. But I do have one final thought, based on something else I read in the paper. They mentioned that while this research offers incredible potential, there are still a lot of unanswered questions and avenues for future exploration. What are some of the big mysteries that remain in this field? It sounds like we're on the verge of some incredible breakthroughs, but we're not quite there yet.
Right.
What are some of those big unanswered questions that scientists are still grappling with in this field?
You're right. This research opens up as many questions as it answers.
Right.
For example,
Yeah.
we've talked a lot about controlling the shape of those internal structures within the glass.
Right.
But what about their composition? Right now, we're mainly talking about creating different shapes within the silica itself. But what if we could use similar techniques to precisely implant different materials within the glass?
So instead of just carving out rooms in our glass house, we're talking about adding furniture decorations, maybe even plumbing and electrical wiring.
Exactly.
Yeah.
We could create entirely new materials with properties we haven't even dreamed of yet.
Wow.
Imagine embedding tiny sensors directly into the glass of your smartphone screen, or creating self-healing materials that can repair microscopic cracks or defects. The possibilities are really endless.
So it's like we're taking the precision of nanoscale 3D printing to a whole new level.
Precisely. And just like with 3D printing, there's also the question of scale. Right now, we're talking about creating these structures on a relatively small scale.
Right.
But what if we could scale up this technology? Could we one day manufacture entire components or devices with this level of precision? Imagine building a computer chip, not by etching circuits onto a silicon wafer, but by sculpting them directly into a block of glass with lasers.
That would be a game changer for sure.
Yeah.
We're talking about really pushing the boundaries of what's physically possible.
Exactly. And that's what makes this field so incredibly exciting. It's not just about understanding the fundamental physics of light and matter. It's about harnessing that understanding to create technologies that were once considered pure science fiction.
It's like we're living in the future that we used to read about.
Exactly.
So for our listeners who want to wrap their heads around the sheer coolness of all this, what's the one big takeaway they should remember from this deep dive?
I think the biggest takeaway is that sometimes the most groundbreaking discoveries come from paying attention to the smallest details.
Yeah.
This research shows that something as seemingly insignificant as the pedestal of a laser pulse can have a profound impact on the final outcome. It's a reminder that we should always be questioning our assumptions, exploring the fringes of what we think we know, because that's often where the most exciting breakthroughs lie.
It's a great reminder to never underestimate the power of a seemingly small detail. Sometimes those tiny overlooked aspects can unlock entirely new worlds of possibility.
Yeah.
Well, thanks for joining us for this journey into the heart of laser physics. Until next time, keep exploring, keep asking questions, and never lose your sense of wonder.
Thanks for having me.
Ever think about how 3D printing, totally changed how we make stuff?
Yeah.
Well, get ready, because we're diving into a tech today with even more potential, maybe way more.
Okay, I'm intrigued.
It's called ultrafast laser writing. It's basically using light to etch super intricate patterns inside materials. We're talking structures so tiny you'd need a microscope to even see them.
It's like 3D printing, but zoomed in a million times.
Exactly. Nanoscale 3D printing, but instead of ink, we're talking crazy short, crazy powerful pulses of light.
And here's the wild part. How we tweak those pulses can totally change what we end up with.
All right, so let's break this down.
Let's do it.
Our source material today is a research paper called, get this, Controlling Ultrafast Laser Writing in Silica Glass by Pult Temporal Contrast.
Catchy, right? It definitely rolls right off the tongue.
So, first things first, ultrafast lasers. What are we talking about here?
Okay, so picture this. A camera shutter that's a million times faster than your phone's camera.
Okay, that's fast.
That's the kind of speed we're dealing with here. These lasers emit pulses of light that last for femtoseconds. That's a fraction of a second, so short it's almost impossible to imagine.
Okay, so super quick bursts of light, but what makes them so special?
It's the energy they pack. These short bursts concentrate a massive amount of energy, and when you focus that on a material like glass, it doesn't just heat it up, it triggers all these crazy interactions at the atomic level.
So we're not just melting the glass, we're messing with its fundamental building blocks.
Exactly. And this is where it gets really cool because the research we're looking at dives into this factor called temporal contrast.
All right, I gotta be honest, the whole temporal contrast thing, it's a bit over my head.
It's a mouthful for sure.
So break it down for me. What is it and why should I care?
Okay, imagine a laser pulse, like a musical note.
Okay.
High temporal contrast is a clean, crisp note. All the energy is packed into a single sharp peak. But some lasers, they're more like a note with an echo.
An echo.
Yeah, so there's this low-power tail of light that follows the main pulse, kind of like a little shadow. We call that the pedestal.
A laser echo. So what's the big deal? We're talking about etching tiny, tiny stuff here. You'd think that echo would get lost in the noise.
Right. You'd think it wouldn't matter, but that's what's so cool about this research. They found that having that low-power pedestal, that echo, can totally change what you can create. It's pretty amazing, actually.
Okay, now you've got my attention. Give me an example.
All right, so lasers with high temporal contrast, they're awesome at creating these tiny, tiny holes in glass called nanopores.
Nanopores. How tiny are we talking?
Yeah.
And what good is a tiny hole anyway?
We're talking crazy small. Imagine storing an entire library on a chip the size of your fingernail.
Seriously.
Nanopores could make that happen. Plus, they're being researched for all sorts of stuff, like filtering water, DNA sequencing, even delivering drugs.
Wow. Okay, so these nanopores are a pretty big deal. So high contrast lasers are the nanopore champs. Got it. What about those echo lasers, the lower contrast ones? What are they good for?
So the lasers with the pedestals, the researchers found they're really good at making a completely different structure. Yeah, they're called lamellae. Picture thin, delicate layers inside the glass, almost like pages in a book, each one just a few atoms thick.
Okay, so we've got these two different lasers making two totally different things inside glass. That's kind of wild. But why? Why would that little echo, the pedestal, change things so much? Shouldn't the main pulse be the one doing all the work?
Right, you'd think so. It's the strong one after all. But that's what's so interesting about this research. They found that those pedestals, even though they're weaker, they can actually mess around with these like tiny defects that the main pulse makes.
Defects? What are we talking about? Like cracks in the glass?
Oh, way smaller than that. Imagine like the main pulse hits the glass, right? And it's like a cue ball, scattering all the other balls on a pool table.
Okay, I'm with you.
So those scattered balls, they're like the electrons in the glass, getting knocked out of place by all that energy.
Makes sense.
And those empty spaces left behind, those are the defects. Specifically, they're called self-trapped holes, if you want to get technical.
We love getting technical.
Right. So the pedestal comes along, and even though it's weaker, it can still mess with these areas that are already like kind of wobbly from the main pulse.
So it's like the pedestal is sneaking in while the glass is still reeling from that first punch.
Exactly. Like it's whispering secrets to those messed up atoms, secrets that the regular glass wouldn't even listen to.
That's a cool way to put it.
And that's how those low contrast lasers with the pedestals can make those intricate layers, the lamellae. It's like even the tiniest things can make a huge difference in this world.
That's amazing.
Yeah.
It's like this whole delicate dance between light and matter, right? Where one little change can change the whole thing. But this research, it was all about silica glass.
Yeah.
What about other stuff? Could you like etch patterns in diamonds with this or silicon?
Yeah, that's a great question. And it shows how exciting this all is. There's still so much to figure out. I mean, this paper focused on silica glass, sure, but it opens up all these possibilities for other materials, you know?
Yeah.
Like imagine creating crazy complex circuits in silicon for like the next generation of microchips, or etching super precise patterns onto diamonds to use in quantum computing.
Okay, so we're not just talking about making pretty patterns here. This tech could be huge.
Oh, absolutely. And think about medicine. Imagine building new organs from a patient's own cells using this. Like we could create these scaffolds for tissue engineering with ultra-fast lasers.
That's incredible.
And then there's like personalized drug delivery. Imagine designing these tiny devices, microfluidic devices, to deliver drugs with crazy accuracy right to where they're needed.
It's mind-blowing to think we can have that much control. But like anything new, there's got to be challenges, right?
Yeah.
What are the big hurdles with ultra-fast lasers?
One of the biggest ones right now is, well, scaling it up. Creating these nanoscale structures, it's pretty slow going, and it can be super expensive.
I bet.
Yeah. So if we want this to be big, like really make a difference, we got to figure out ways to make it faster, more affordable, so we can use it on a large scale.
So it's not just about understanding the science. It's about engineering, too. Figuring out how to actually make this stuff work in the real world.
Yeah, exactly. We have to bridge that gap between the research lab and the factory floor. And that takes everyone working together, the scientists, the engineers, even the entrepreneurs who can see the potential and run with it.
This is why I love doing this show. We can really dig into not just what's possible, but also like how we get there, you know?
Absolutely. It's about the whole journey of discovery.
And in this case, the potential for ultra-fast lasers. It's huge.
Totally agree. And the most exciting stuff, we haven't even thought of it yet, I bet.
It's like we're like peeking into the future of, well, everything.
Yeah, and it's really mind-blowing when you think about it. This whole thing with temporal contrast just shows that even the smallest details can make a massive difference, you know? We're not just blasting lasers at things. We're like orchestrating this intricate dance between light and matter.
Orchestrating. I love that.
Yeah.
But where do we go from here? What are the big mysteries, the big questions that researchers are still trying to figure out about ultrafast lasers?
Well, one of the biggest ones is control, getting even more precise. Right now, we're making stuff at the nanoscale, but what about going even smaller, like to the level of single atoms? Right. Imagine what we could do then. And then there's the complexity factor. Can we use these lasers to make like not just static structures, but things that can change, that are dynamic, materials that can like heal themselves or adapt to their environment?
Okay, now that sounds like something out of a movie.
Maybe. But hey, maybe that's where all this is heading. And that's what's so exciting about this field, you know? It's all about pushing the limits of what we think is possible and discovering whole new frontiers we never even knew were there.
This whole deep dive has been like that, honestly.
Oh.
We started with these laser pulses, and now we're talking data storage, building organs, the future of computers.
It's crazy, right?
It's amazing how it all comes back to life.
It really is. And the more we learn about it, the more we realize we don't know. Every answer just leads to, like, a million more questions. But that's what makes it so awesome,
Totally. So for anyone listening who's ever felt limited, like they didn't have the right tools or whatever, remember this. Sometimes the biggest breakthroughs come from understanding the smallest things and then figuring out how to use them in ways no one ever imagined.
Couldn't have said it better myself. Those tiny details, they can change the world.
Well said. And on that note, that's a wrap on our deep dive into the world of ultrafast lasers. Thanks for joining us, and until next time, keep exploring, keep learning, and keep those laser beams focused.
Imagine, like, etching these intricate designs onto a piece of glass, but they're so small they're practically invisible. We're talking designs measured in billionths of a meter. That's the kind of wild world we're getting into today, diving deep into ultra-fast lasers and how they can change silica glass in ways we never really, expected.
Yeah, and what's really blowing my mind is we're not just talking about making existing tech smaller. This research, straight from the Optoelectronics Research Centre, suggests we're maybe, like, on the edge of creating materials with totally new properties. All because we're starting to understand how these lasers mess with matter on such a tiny scale.
So we're talking potentially revolutionizing how we do, well, everything. Data storage, healthcare, all by messing with glass at the nanoscale. Our source material gets seriously deep into the weeds on this, so we're here to, make it make sense.
Right. We'll be your guides through this whole world of femtoseconds, which is, like, hold on to your hats, 1/4 of a second. And we'll unpack why this thing called temporal contrast is the key to unlocking what ultrafast lasers can really do.
Okay, femtoseconds, temporal contrast, those are some big words. Maybe we should, start with the basics. What even makes ultra-fast lasers so special in the first place?
In the simplest terms, it's all about how short the light bursts are. Think of a normal laser like a steady beam, right? Like a hose spraying water. An ultrafast laser, more like a quick burst from a water pistol. That super short pulse lets us change materials in ways we just couldn't before.
So it's not just heating things up, which is what happens with longer laser pulses. These ultrafast lasers are like changing the structure of the material.
Exactly. And when we say ultrafast, we mean it. To give you an idea, a femtosecond compared to a second is like comparing a second to 32 million years.
Yeah.
Crazy, right? Imagine trying to take a photo of a hummingbird's wings while it's hovering. With a normal camera, blur, right? But with a camera that takes pictures in femtoseconds, boom, you freeze those wings and see every tiny detail. That's the kind of precision we're talking about here.
Okay, that's mind-blowingly fast. But what's all this got to do with silica glass? What makes it so interesting to researchers who are using these ultra-fast lasers?
So, silica glass, basically purified silicon dioxide. It's everywhere in tech. Fiber optics, microchips, you name it. It's transparent, it's tough, and it has these unique optical properties. But here's the kicker. For the longest time, scientists thought the way to change silica glass with lasers was just hit it with more power. But this research throws a wrench in that. It shows that this thing called, remember, temporal contrast, well, that really matters.
All right, temporal contrast. Sounds important, but I gotta admit, it's a bit confusing. Break it down for us. What's it even mean when we're talking ultra-fast lasers?
Okay, so picture a laser pulse like it's a wave, right? But instead of a nice, smooth, single crest, it's got this little bump before the main wave. That's the pedestal. Temporal contrast is basically how big is that bump compared to the main wave? How, clean is the laser pulse, High contrast is like a super precise chisel, nice and clean, tiny pedestal. Low contrast is more like a hammer, gets the job done, but it's messier, bigger pedestal.
So a clean, high contrast pulse versus a messier one with that pedestal. Why is that such a big deal?
Because, get this, the research shows that even though that pedestal is weaker than the main pulse, it can totally change how the laser messes with the silica glass. We're talking unexpected modifications here.
So it's not just raw power anymore. It's about being precise, controlling the shape of the pulse. And this tiny little detail, this pedestal, can totally change the outcome. All right, now that we've established how important this whole pedestal thing is, let's get into how it actually changes how we can use lasers on glass at the nanoscale. So, like we promised, let's dive into these crazy modifications these ultra-fast lasers can pull off. The paper talks about different types, giving them names like type X, type 2 meter. Sounds like we're sorting through, I don't know, space rocks or something.
Right. But think of it this way. You can create different, I guess you could say, flavors of modifications in the silica glass. It all depends on your laser settings, especially that temporal contrast we talked about.
Okay, flavors of modifications. I like that. So what's really different when we compare those high contrast lasers, the really precise ones, to the ones with a big pedestal?
Well, one of the biggest differences is making those nanopores we talked about.
Hmm.
The type X modifications. They're like, imagine tiny bubbles, but inside the glass. These nanopores, they could be used for all sorts of things. Super sensitive sensors, maybe even detecting single molecules, or filters with incredibly, and I mean incredibly tiny pores.
So high contrast lasers, we're talking about etching out these empty spaces, these nanopores. What about when we use a laser with lower contrast, the one with the big pedestal? What happens then?
That's where things get really interesting. Instead of those precise nanopores, the low contrast laser, it makes these, well, the study calls them type 2 meter modifications. They're not really like separate bubbles. They're more like these thin sheets inside the glass, almost like layering the material, you know?
So it's like, I don't know, carefully carving out a tiny space versus like slicing into the material to make a thin gap. And it all comes down to that initial bump, the pedestal.
Yeah, exactly. It just goes to show even the smallest difference in the laser pulse can completely change what happens. And remember, we're not just talking about making these structures. It's about controlling how big they are, what they look like, even where they are inside the material. That level of control, that's what's really exciting for new tech and applications.
This is seriously cool stuff, but like, what's the big deal here? Why are we so obsessed with changing glass on such a tiny scale?
It is a big deal, right? The possibilities are, well, pretty much endless. This research, it could change everything. Material science, optics, photonics, it's huge. Imagine like storing tons of data, maybe even the whole Library of Congress on a tiny chip.
Hold on. You're saying our smartphones could have more storage than a supercomputer just by using lasers to etch these tiny patterns in glass?
Yeah, and that's just the start. Think about healthcare. We could make these super complex microfluidic devices, like unbelievably precise, for diagnosing diseases from just a single drop of blood, or delivering drugs right where they need to go, individual cells even.
So we could revolutionize, let me see, data storage, healthcare, who knows what else, all because we're zapping glass with these lasers.
It's definitely going on my top 10 coolest science things list.
And the best part, we're just getting started. We're just starting to understand how light interacts with stuff at this scale. Who knows what we'll find? This research just shows how a tiny detail, the shape of the laser pulse, can open up a whole world of possibilities.
It's like, it really shows how the smallest things can lead to the biggest discoveries in science. So as we wrap up our deep dive into ultrafast lasers and their surprising effects on silica glass, what's the main takeaway you want our listeners to remember? You know, I think it's all about understanding and really controlling light. Like at the most basic level, we think of lasers as these powerful tools, which they are, but they're also super precise. We can use them to manipulate matter in ways we never even thought of before. And the more we push the limits of what lasers can do, the more we learn about light. Well, the future of all this, material science, optics, photonics, it's looking brighter and smaller than ever.
It's like we've got this whole new toolbox and we can build the future one femtosecond at a time. And for anyone listening who's just as, I don't know, amazed by all this as I am, here's something to think about. What if we could actually control that pedestal effect? Like use it on purpose to create even more complex nanostructures, things with properties we haven't even imagined yet. Keep that in mind as you keep exploring this whole world of ultrafast lasers and everything they're showing us about the nanoscale.